Chancellor His Excellency Dr. Thabo Mbeki, the titular head of the university, the Vice Chancellor and Principal of the University of South Africa, Professor Nkambule, to the professor that we are inaugurating this evening, Professor Thabo Nkambule, his family members, friends, and loved ones, members of the College of Science, Engineering and Technology, the college management, the staff, the academic and administrative colleagues, staff at large, UNISA students and visiting students from other higher institutions that we associate with the partnerships that we have through the work of Thabo Nkambule, distinguished guests, boys and girls. Again, most importantly, Prof. Thabo Nkambule, a celebrity of the day. Sanbonan, Avwan, Dumelang, Tobelang, good evening, Goeienaand. I acknowledge you all. My name is Professor Tenjiwe Meyiwa. I'm the Vice Principal responsible for research, postgraduate studies, innovation and commercialization. I welcome you to Prof. Nkambule's inaugural lecture. Prof. Nkambule is affiliated with the College of Science, Engineering and Technology as the head of the Institute of Nanotechnology and Water Sustainability. Please allow me to congratulate him, but also acknowledge the Executive Dean of the College, Professor Mamba. I also acknowledge and welcome our respondent, Professor Jarvis, who is a professor of water science and technology at the Cranfield Water Science Institute in the UK. He serves as a respondent during this installation. We thank you, Prof. Jarvis, for heeding our call to serve as a respondent for this lecture. Now, ladies and gentlemen, boys and girls, you will agree with me that the country, the globe, the higher education sector is faced with a myriad of challenges, one of which is that which Prof. Nkambule has isolated through his scholarship to respond to, which relates to water sustainability, which relates to the innovation within that. Don't want to spoil his lecture because you'll be learning more when his boss, Prof. Mamba, comes to the stage and when he delivers his lecture. But it's a lecture whose content is very important and significant and very much relates to the work of the African Union, taking a leaf, of course, and reverberating the United Nations Sustainable Development Goals, and by extension, endorsing and responding to one of our catalytic areas that our Vice Chancellor, Professor Nkambule, has wanted us to uplift and respond to. As an institution, we very committed and must produce the kind of research through such heads of institutes like Prof. Nkambule and his work. And aside him being the head of a research institute, he's produced and mentors junior researchers and postgraduate students whose work center around what he's going to share with us this evening. It is for that reason that, therefore, occasions like these ones of inaugural lectures, we take them seriously, and they are proud moments, moments that we are very heartened by the fact that we're growing our research expertise and we're becoming more real, effective, impactful to the challenges that we have on the ground within our societies. That's a full professor for you. Now, what is a full professor? A full professor is somebody who's gone through all the ranks and stages of the academic life to a rank that is actually the highest, or one amongst the highest. It's somebody who will have mentored, produced research, reproduced research, produced postgraduate students, mentored them to a level that we expect, has raised funds, and ensures that the university's research agenda is sustained. I invite you to congratulate Prof. Thabo Nkambule through the chat box comments with words of encouragement for the work that he's produced that's led him to be a full professor. As it relates to the proceedings that we're going to have this late afternoon, early evening, we will have Prof. Mamba on the stage to introduce Prof. Nkambule. After him immediately, we'll have Prof. Nkambule, and who will then be immediately followed by the respondent, Prof. Jarvis. I will not be coming in between these colleagues so that we have a flow of this lecture that promises to be very interesting. So at this juncture, I want to present to you Prof. Mamba as I invite him to the podium to let us know about who Thabo Nkambule is. Over to you, Prof. Mamba.
Acting Vice-Chancellor, Professor Thenjiwe Meyiwa, who is the Vice Principal for Research and Innovation, Postgraduate Studies and Commercialization at the University of South Africa, I would like to acknowledge your presence. And I would also like to acknowledge the presence and the attendance of the members of the College Executive Committee of the College of Science, Engineering and Technology, colleagues at CSET, both non-academic and academic staff. I would also like to pay special homage and respect to distinguished guests who are following this inaugural address, and collaborative partners of the University of South Africa, specifically the College of Science, Engineering and Technology, even the Institute for Nanotechnology and Water Sustainability. I also like to acknowledge the presence of Professor Peter Jarvis, who is a professor at Cranfield University in the United Kingdom, who will be the respondent to the inaugural address to be delivered by Professor Nkambule. Professor Jarvis is an academic associate of the University of South Africa and collaborates with Professor Nkambule in the course supervision of postgraduate students at the Institute for Nanotechnology and Water Sustainability. I would also like to pay special respect and welcome to Thabo's family, specifically Busi, who is his wife, and his son Luyanda, his brothers and sister, and his mother, who are in this particular meeting this afternoon. A special welcome to them and to the family at UNISA. I'd also like to acknowledge the distinguished guests who have been invited by Professor Nkambule and also his friends who have been supportive to his journey to becoming a full professor. And therefore, I would also like to acknowledge Professor Thabo Nkambule by reading his citation. It is therefore my pleasure this afternoon to read the citation of Professor Thabo Thokozani Innocent Nkambule, who obtained his Doctor of Philosophy degree in chemistry at the University of Johannesburg in 2012. After completing his doctoral degree, he then went on to pursue his postdoctoral studies at the Technical University of Delft in Netherlands from October 2012 until December 2013 under the mentorship of Professor Bas Hyman, where he was responsible for developing stimuli modeling techniques for the application and prediction of the type, character, and composition of natural organic matter in any urban water cycle system. In 2014, Professor Nkambule was appointed as a lecturer at the University of Johannesburg, where he was involved in the teaching of analytical chemistry and chemical quality assurance to undergraduate students across different faculties, while pursuing research on developments of methods of improving water treatment efficiencies in South African water treatment plants, with special emphasis on the removal of natural organic matter and emerging pollutants. Professor Nkambule then joined the University of South Africa as a senior lecturer on the 1st of September 2014, where he is a leading special research group leader in water treatment research under the urban water cycle, where they deal with water treatment technologies which mitigate natural organic matter and disinfection byproducts which are present in water systems. He is currently the head of the Institute for Nanotechnology and Water Sustainability, which is known as INANOS. Historically, he was the founding member of the then Nanotechnology and Water Sustainability Research Unit, where he worked closely with the founding director of the NANOS Research Unit, where he set up policies and procedures for operation of the unit, as well as in ensuring that the laboratory infrastructure was in place for the students to be admitted to the research unit. During his tenure as a senior lecturer, he has received multiple research grants as a project leader and as a co-investigator, among which are the Water Research Commission Research Grant to the value of 1 million rands, and has also been the recipient of the Vision Keepers program to the tune of 860,000 rands, and is a co-investigator to the BRICS Multilateral Joint Science and Technology Research Collaboration Project, whose value is 2.1 million rands. Prof. Nkambule was promoted to the rank of Associate Professor at the University of South Africa and subsequently appointed as the Acting Director of the newly approved Institute for Nanotechnology and Water Sustainability, which is popularly known as INANOS, a position that he has held since December 2020. At the beginning of 2021, Professor Nkambule was appointed as a full professor at the University of South Africa, and in the same year, he was recognized by the NRF with a C3 rating. And furthermore, he was formally appointed to be the head of the Institute on a 3-year secondment, and a job which is actually doing with great aplomb and great satisfaction to the college. I would like to mention that as much as Professor Nkambule is the head of the Institute, he is an established scholar who has published over 80 journal articles in peer-reviewed journals and has graduated 15 master's students and 3 PhD students, as well hosting 4 postdoctoral research fellows. He is currently involved in the supervision of 14 postgraduate students who are either pursuing their master's degrees or doctoral degrees. He has presented his research work at numerous national and international conferences, either as a plenary speaker, keynote lecturer, or just making an oral contribution In addition to the research efforts mentioned above, Professor Nkambule is registered with the South African Council for Natural Scientific Professions, known as SACSNAP, as a professional natural scientist. He is also a member of the Water Institute of Southern Africa, WISA, and a member of the International Water Association and a member of the American Chemical Society. Professor Nkambule is eternally grateful for the support he has received from his family and loved ones throughout his career, and therefore would like to acknowledge their presence in his inaugural lecture today. This accomplishment is also largely as a result of the considerable efforts of his mentors, students, colleagues, and many of his research partners, for which he is grateful to all of them. Ladies and gentlemen, I would now like to invite Professor Thabo Nkambule to present his inaugural lecture. Thank you very much.
Good afternoon, ladies and gentlemen. Professor Thenjiwe Meyiwa, the Vice Principal for Research and Innovation, Postgraduate Studies and Commercialization. Professor Bheki Mamba, the Executive Dean of the College of Science, Engineering and Technology. My family present, senior leadership of the university, students, ladies and gentlemen, all protocol observed. I will be speaking to you today about abundance, scarcity and innovation, a water quality tripartite alliance centered on natural organic matter, which forms part of my research core over the years. Of course, before I begin, it is important on an occasion such as this to start off by acknowledging family, the people who have been there for me through very early ages. My mother turned 60 a few days ago, and my brothers and my sisters, Tembega Maki, Kuku, as well as the lady of my life, Busi, together with my son, Yandu. Ladies and gentlemen, the issue of water scarcity needs to be looked at starting from the surface and groundwater sources in the country, as can be seen in the map here, that 22 water source areas in South Africa are on 8% of land, providing 50% of our surface runoff. If you zoom into the provinces in terms of national vulnerability, statistics taken from the water services challenges, you can see that South Africa is largely water scarce, especially the Western Cape and the Eastern Cape, as well as to a larger extent the Northern Cape and the Free State, as can be seen on the photo on the right, which is what was the case about 2 years ago. In fact, if we move to the year 2019 in November, we will see that in terms of the provincial dam levels, the Eastern Cape was sitting at 48.8%, the Western Cape was sitting at 66.5%, and Gauteng was sitting at 85.3%. If we then move into the 17th of January 2022, we see a dramatic twist where the Western Cape still is at low of 63.2% and the Western Cape at 78.1%, and Gauteng actually have 104.5%. And one of the issues then, therefore, which we need to look at is how do we move from drought as well as to floods, which is currently what we are seeing on these days, and what are the impacts on water sources and water quality of the same. And one of the things that is important is to look at the paradigm shift in water supply, where we stop looking at certain issues as wastewater sources. For example, there is a lot of mining in South Africa, and we have a lot of what is called acid mine drainage. We have the oceans in South Africa, which we look at issues of desalination, production of drinking water from the oceans, as well as return flows from irrigation and stuff. And we need to start looking at all of these water sources holistically. And as if that was not enough, there is what is called natural organic matter, which is an impossibly complex matrix that varies temporally and spatially. And natural organic matter is formed from the natural degradation of plant and animal material into various water streams, and it forms then the backbone of water treatment, because it varies from region to region based on the sources as well as the vegetation and the climate as well as the weather of where we are at that particular time. It also influences various properties of water treatment, such as charge, molecular weight, hydrophobicity, and reactivity, which I'm going to speak about. And therefore, no one method can be suitable for treating this type of natural organic matter, depending where you are. You can't apply a one method for all the geographic locations of the country, South Africa, for example. And in more detail, if you look at the water treatment process, where water comes from sources, water with lots of natural organic matter often looks brownish and yellowish. And if that water then is taken into a water treatment plant, and one of the processes to treat water is coagulation, flocculation, which is aimed at removing particulates as well as other dissolved organic matter. And if there is organic matter present there, it affects the treatment process in the sense that too much of it present will mean that we have to add more coagulants, and therefore making the process very expensive. And conventional water treatment processes do not remove sufficiently the natural organic matter before filtration, before disinfection. And in South Africa, we use chlorine for disinfecting. So if this natural organic matter is present at the disinfection stage, it reacts with disinfection byproduct, it reacts with the disinfectants, forming disinfection byproducts, which are mutagenic and carcinogenic. And also, in terms of the supply of water with natural organic matter present in the distribution system, it causes biofilms and the corrosion of the distribution system. And what does this natural organic matter look like? It looks like a clustered accident on the N1. You can imagine different types of cars in the N1, lorries and trucks and buses in an accident all together. But what we then have to do is to find ways of separating it, as you have seen there, and we call that the fractionation of natural organic matter, so that then it can be fractionated from the complex mixture that you see into the various components that constitute it. And that fractionation is done through various methods that we'll talk about today. So what do we do then? What have we been doing in the past 8 years or so? We call it our approach for the urban water cycle and water treatment technologies. And as you can see, the first important thing there is to develop protocols for identifying what this natural organic matter is, and we call that natural organic matter characterization. From there, you look at various methods of removal as well as treatability, looking at the conventional processes that are currently applied and how then we can modify those using advanced techniques, as well as upscaling the technologies, therefore, and resource recovery. And my inaugural lecture, therefore, will then be speaking in terms of those three things. What have we been doing in the past 2 years? What are the questions? And what is the future? The norm characterization, the removal and degradation methods, norm treatability, as well as optimizing conventional methods, also in line looking at advanced techniques. And obviously, because we are a research institute, we look at upscaling institute as well as dealing with means of resource recovery. So the first thing over the years is that we've been plotting a water map of the country where we've sampled in the various regions of the country to define what type of natural organic matter occurs, so that if we know what type of natural organic matter occurs, we are then able to then develop methods to treat that. And we've done this with various students in the past who have either graduated for their master's and doctoral studies. One of the techniques that is key to my heart is what is called fluorescence excitation emission matrices, which gives you a map which you are able to plot the various organics present in the water in terms of the humics, the fulvics, the tritophin, which are the proteins, and the tyrosine. And I'm pleased to say that we are the only ones in the African continent who have invented and worked with Horiba Scientific in developing this method. And in so doing, then, we are able to look at colored dissolved organic matter, which is called CDOM, where you can classify and quantify the amount of humics, high molecular weight hydrophobics, aromatics absorbed by coagulants, as well as compare with the low molecular weights and stuff associated with wastewater effluents. And an example of that is a project which was done by Ms. Sigelo Landiweni for her master's, where she looked at feed stream analysis to identify the type and character, to fractionate into various fractions, and determine the treatability influence of each. And we did that with Professor Adam Gilmore from Horiba Scientific, who is seen in the photo on my right in our laboratories. And we were also then working with Professor Stijn van Halle from the Ghent University in Belgium, where we developed three-dimensional correlation between natural organic matter in its heterogeneous mixture, absorbing behavior and activated carbon. And together with Professor Namo Chaukura, who was our postdoc at the time, and now works at the Solplaatje University. And the work has been published in the Environmental Technology, where the title was Accessing the Impact of Environmental Activities on Natural Organic Matter, comparing South Africa and Belgium, as well as coming up with the variance fractions based on the themes as well as the MATLAB. So what are the research questions and the research gaps that we are looking at? One of the most important things is to be able to define the property of influence. Looking at the coagulation, it is based on charge and hydrophobicity. Looking at the ion exchange, which is based on charge molecular weight. Looking at the membranes, which is charged on molecular size, hydrophobicity, and then being able to define this property of influence versus what it can do. An example here is a sample from the Plettenberg Bay water treatment plant, where the top right figure shows what the film contour plot looks like with those organics. And as you can see, moving from the top figure to the left and to the right, the removal of the organic matter through the process. Secondly, we want to ask ourselves, what should an ideal measurement of dissolved organic matter tell you? It should tell you issues of treatability. Is it removed by the different water treatment process? What are the impacts on the processes for removing? Will it influence the performance of other processes? What are the downstream activities, as well as the prediction based on models? Can it be measured online? And what are the control systems? But most importantly, what we have done is also to develop a rapid tool to identify norm treatment limits achievable by any method. And these tools must be robust, must be portable, and definitely for the South African context, must be inexpensive. So how do we go about understanding the treatability? The treatability defines what are the impacts of this organic matter in the water treatment process. And we give an example of the treatment there, from raw water to filtration, looking at destabilization, flocculation, solid separation, and finally filtration. If there is a high amount of natural organic matter, you expect then that if your coagulation flocculation is not that efficient, there will be high disinfection byproducts. If you are using membranes, there will be membrane fouling, higher coagulate and disinfectant dosages. So we also have to look at the biodegradability of norm. What is the biodegradability of norm? To see how much of NOM can be removed through biodegradation processes. And we've done this work with Randwater, working with Dr. Espa Nkambule from Randwater, and two of our students who have graduated there, Safia Marey on the bottom right, who graduated for a PhD in 2019, as well as Mr. Sfiso Sambo, who graduated for a master's in 2020. They looked at issues of simultaneously measuring the biodegradable dissolved organic carbon, looked at identifying the problematic norm fraction, as well as developing characterization techniques for so doing. And this work resulted in a publication on Journal of Water Process Engineering, where the method employed is now being currently used at the Randwater for determining the biologically degradable organic carbon, as was designed by Mr. Sfiso Sambo and Dr. Espa Nkambule. Dr. Safia Marey. And of course, we also work with the Cranfield Water Science Institute with Professor Peter Jarvis, where we look at determining the properties of NOM. And as I showed in the graph earlier on, you can be able to fractionate NOM into the various fractions of hydrophobic, hydrophilic, as well as the transphilic fraction. And the hydrophobic fraction, which means the fraction is mainly made of humic substances, is actually easy to remove through coagulation. And the hydrophilic fraction is easy. It's difficult to remove through coagulation, as well as then the transphilic fraction of both is very difficult to coagulate. And then this knowledge, as we're working with the Cranfield Water Institute, also assist us in looking with issues of low color, moderately hard water, where you can compare the hydrophobics and the hydrophilic and then determine which type of flocculation, for instance, to use, comparing that with the difference in dissolved organic matter removal. And then you can be able to put cost of pH correction, what we call enhanced coagulation, and so often reduced DOC removal is accepted, while the hydrophilic low trihalomethane formation potential is probably low. Now, once you understand the character, you then need to understand and control the impact of this NOM in engineering systems. And one of the most important things is to look holistically at the urban water cycle and water treatment technologies. And I use a diagram here thrown by one of my master's students, Ms. Sleswane, who was actually looking at de facto water reuse through the cycle of water from the sources into drinking water treatment process, into the usage by different users, back into the water treatment processes, and then being disposed into the rivers. And we then look at what type of prevalent compounds can be found there. And one of the things then that we need to understand also is the competition of binding sites on adsorbents. For example, if you are removing NOM, using adsorption or absorption, because of the size of the NOM, it does compete for adsorption sites. And we have published some work on that as early as 2008. And other colleagues, especially Newcomb, have looked at simultaneous adsorption of MIB, which is responsible for the odor, as well as NOM onto activated carbon. In one of our collaborations, we collaborate with the University of Massachusetts through Professor David Rekau, and we look at NOM and disinfection byproduct control, especially looking at natural organic matter being present through disinfection with chlorine, where we look at issues of halogenated disinfection byproducts as well as the non-halogenated disinfection byproducts, and compare that with the South African National SANS 2401, which is the standard body controlling the quality of water in the country. Specifically, if you look at a natural organic matter fraction with the three different fractions of hydrophobic, hydrophilic, transphilic, and then with chlorine present through disinfection, it forms disinfection byproduct, mostly trihalomethanes and haloacetic acids. But the characteristics of the NOM, the disinfection parameters as well, also control that. And the question then is, what is the process and how is that process controlled? And also, which of this fraction is present in greater proportions and which of the fraction is responsible for the different performance in the stages, as well as using fractionation to identify problematic norm fractions, thus informing the choice of methods to apply then effectively alternative combination regimes or specific treatment technologies. And with Professor Rekau, for instance, they look at the importance of dissolved organic matter reactivity on the incorporation of bromine and iodine in disinfection byproducts produced during chlorination and chloramination. And depending on the SUVA, which is a measure of the hydrophobicity, you will be able to see in terms of the concentration sites and the reactivities in the formation of what type of disinfection byproduct. So we have a postdoctoral fellow by the name of Dr. Ali Ilunga, who has looked at dehydrogenation of halogenated disinfection byproducts for clean drinking water, and has published extensively his work, also looking at nanocatalyst and disinfection byproducts degradation, which he has fashionably called nano-DBPs. He also looks at ferricyanide reduction to elucidate kinetic as well as electrochemical activities on the metal surfaces. We, on the side of membrane work, as one of the technologies, work with Dr. Mota on aspects of high performance membranes for the NOM removal. We look at issues of membrane preparation, specifically for the membranes which work on permeability, to look at a laboratory scale various fabrications of these membranes which will be geared towards removing different types of NOM. We have also taken this to use natural resources in terms of enzymes and fungi to culture growth and enzyme extraction, so that then we are able to evaluate the membranes for suitability in terms of removal of our NOM and pharmaceuticals, and then using various aspects in terms of coupling agents and all of that, with the sole aim of catalytic degradation and removal of natural organic matter and pharmaceuticals. Ms. Pumlile Mamba therefore graduated for her master's looking at lacase-coated polythiosulfone membranes for organic matter removal, where she picked white rot fungi from the forest and then was able to culture and apply that for biotreatment of biomass, water and wastewater treatment, degradation of dyes, biopulping and biopleaching, especially looking at the lacase mechanism of that. And she worked with a postdoc fellow from the College of Agriculture and Environmental Sciences. And she was able then to do the fungal isolation and enzyme extraction of this, which we then used for developing a method to embed these enzymes into our membranes and then be able to remove the natural organic matter using it. And this work was published in the Journal of Membrane Science and Research. Also, still talking about membranes, we look at issues of hybrid system development, where we want to do various permutations of membranes coagulation and membranes advanced oxidation processes, so that we look at the combined removal of NOM fractions and pharmaceuticals. And my PhD student, therefore, Mr. Fanon Thindane, looks at the monitoring and removal of emerging micropollutants and natural organic matter through high flux membranes. And he has spent some 6 months at the Massachusetts University in the United States. And there is quite a number of publications coming from that, where we have developed these membranes that look at humid exit fractionation of NOM, interacting better with the EMPs, as well as a rapid phase invasion, producing highly permeable membranes, as well as hybrid systems, enhancing the removal of this natural organic matter. We also, in the past, have worked with the Technical University of Delft in the Netherlands, where I actually did my postdoctoral fellowship, where we look at issues of unlocking the potential application of South African clays to the water treatment industry. Professor Pass engineered a system called atomic layer disposition, working with my then PhD student, Weldon Moyo, where we then look at tampering with the layers of the membrane through the atomic layer deposition process for removal of natural organic matter. And of late, we are looking at the issue of introducing ceramic membrane filtration, and Weldon is working on that in the lab and has already produced ceramic membranes from clay. And we are currently testing these clay ceramic membranes for application in a real setup. And we are working with Makhali's Water in South Africa for so doing. And therefore, we look at this integrated process: coagulation, absorption, and membrane filtration. And one of the most important factors that is currently a question going forward is which of the natural organic matter fractions is responsible for microfiltration and ultrafiltration membrane fouling. And understanding membrane fouling is very important, because every membrane, as you know, works through a permeable layer to allow water of certain quality to pass through while removing what you want to remove. And because of the size of natural organic matter, it often blocks those pores and prevents then the membrane from actually doing what it's supposed to do. And that concept, we call it membrane fouling. And understanding which of the natural organic matter fraction is responsible for that is important, so that we are able then to tailor make the membranes to target those fractions rather than looking at it holistically. As I draw towards the end, one of the questions that we look at is exploring advanced oxidation processes for natural organic matter removal, where we look at the production of hydroxyl radicals which react with organic pollutants, degrading it to carbon dioxide in full or partially. And one of the issues that's globally spoken about is that the toxicity of the degradation byproducts. And therefore, we look at the mechanism that we introduce using advanced oxidation processes, but also being able to study what are the toxicity of what we are trying to produce. And we have various AOPs that we're looking at. And that work, we have been channeling it with my postdoctoral fellow, Dr. Gina Mamba, who has worked with one of my master's students, Ms. Lerato Moas, who also spent some 6 months at the Cranfield Water Institute working on ultrasonic assisted synthesis, for example, of binary nanocomposites for photocatalytic water treatment, with the aim to design and prepare visible light active photocatalysts using ultrasound assisted synthesis for the abatement of emerging pollutants in water. And we look at different catalysts, looking at a combination of the binary nanocomposite, the characterization to confirm indeed that we have formed a binary nanocomposite, and finally doing the photocatalysis visible light applications. And this work has produced a minimum of 3 papers in the last 5 years, as published in colloids and surfaces, as well as other high impact factor journals, as you can see in the slides. And finally, we also have to bring the research to the communities that we serve, because then doing research only in the labs is not that much impactful, but of course you have to prove the concept in the lab. And one such project is determining the extent of de facto water reuse in South Africa, the case of cities in Gauteng, Western Cape and KwaZulu-Natal. And this project, as I said earlier on, was done by my master's student, Ms. Swane, where she has sampled in various wastewater treatment plants following the urban water cycle, where we look, for instance, in Town 1, we look at a river that is upstream of a wastewater treatment plant, and we sample there, and then sample downstream of that river, as well as sample within the wastewater treatment effluent itself, with the aim of seeing how effective the wastewater treatment plant is in removing target pollutants. And in this case of Umhle, we used caffeine, and we used an antibiotic, as well as used an antiretroviral drug, which our water treatment plants were not designed to remove. And then we can be able to see indirectly how much water is being reused. And this work was done with Professor Peter Smith from, again, the College of Agriculture and Environmental Sciences, which sits in our campus. And of course, then we develop a model which we call a de facto reuse model, which has been slightly modified by Ms. Swane, where we're able to calculate the model for the wastewater tracers. And the prediction here is that then with this calculation, we will be able to see the effectiveness of what our plants are doing, as well as how then we can assist in remodifying and redeveloping for them to catch up with the times. And we're grateful for the city of Johannesburg through Johannesburg Water, as well as Umgeni Water in Durban, as well as the Buto municipality in the Western Cape, and Plettenberg Bay in the Western Cape, who have given us access into their laboratories, as well as into their water treatment plants, so that we are able to test this work effectively in a live environment. And again, this work has resulted in a publication in a high impact factor journal, as well as has gotten some international recognition through various presentations, as this was the first of its kind done in the South African context. Finally, one of the new technologies that we are looking into in terms of innovation is looking at sensors, electrochemical sensors, which do 2 functions, which is detection and degradation. Sensors are a new technology, and therefore are not that much used because of expenses and stuff like that. But working with our colleagues within the Institute, Dr. Fagayode, my postdoctoral fellow there, as well as Dr. Usese Feleni, the thematic area leader for applied electrochemistry, we're looking at materials and methods for developing and looking at non-solvent phase separation, for example, similar to membrane casting, using water as a solvent. We have been able then to come up with electrochemical sensors, and Dr. Fagayode has communicated this work, which he often calls sustainable materials as sensors degrading tools for natural organic matter removal. He has published within 2 years this work in 6 journal articles, as you can see in the slides. Ladies and gentlemen, this now brings me to the end of my talk. And you can forget everything that I've said thus far, But there are only 4 things that you must not forget, and I've called these the key points to remember. The first one is that natural organic matter is a complex, heterogeneous mixture that is not only hopelessly complex, but progresses faster and defines our water treatment regimes. Very difficult to characterize and categorize based on underlying structural features rather than methods of extraction. And also then the recognition and being able to develop methods to quantify and qualify this is part of the research questions that will be forever going on in our research. And also that the different sources, therefore, number 2, they set the stage, whether the source is terrestrial, atmospheric, or aquatic, or as well as anthropogenic. They set the stage on how then we define our water treatment regimes. Obviously, because we live in changing times, the processes then change the outcome. The natural system, whether aerobic degradation or anoxia, sediments also change this. And also aligned with that is the role of climate change in the methods that we develop. How do they affect the issues of climate change? We must be careful of that. And finally, going back to the title, as it was abundance, scarcity, and innovation. And I've tried to demonstrate to you the type of innovation and adaptability in this field that we have embarked on, where we look at new and emerging trends, especially living in the South African context where we are not that much of a rich country, to look at cost, effectiveness versus performance using the abundant natural resources that are at our disposal, and also looking at the issues of abundance. How do you then quantify that abundance versus scarcity? I gave an example of the dam level in 2019 compared to 2020, 21, and with these very erratic weather patterns that we are seeing going forward. Obviously, colleagues, I end by thanking all my past and present students and postdoctoral fellows. As I've seen, as I've put in these photos, some of them are not there. To my students and to my postdoctoral fellows, I am because you are, and I wouldn't be where I am without your input that is valued, and we continue engaging each other robustly in the academic space, where we agree and disagree, because the concept of teaching students is that we as staff members are not the holy trinity of education, but we also learn from our students. And it's been a pleasure supervising the more than 15 master's students to completion in the last 3 years, as well as 3 PhD students, as well as 4 postdoctoral fellows, whom you can see with various selfies and stuff in the photos and slide. And I wouldn't be where I am without my supervisors. So to my PhD supervisors, Professor Begi Mamba, who has shaped the academic that I am over the years. He supervised my master's and supervised my PhD. Professor Johannes Haroff, who is a retired civil engineer, and also introduced me slightly to the world of civil engineering while being a chemist by profession. And Professor Rui Krause, who now is the head of Department of Chemistry at the Rhodes University. The 3 gentlemen shaped me as a master's student and as a PhD student, and introduced me to this topic, which I've then taken, I've moved further. And without them, Professor Mamba, Professor Haroff, and Professor Krause, I wouldn't be the academic that I am. To you, I'm forever indebted. To my partners, academic partners, that is strategic as well as from the industry, there are so many of them, I wouldn't be able to list them. The South African water industry, the international academia, as well as the national academia, as listed there. Thank you so much for the good collaborations over the years. And we can only say more is coming. The sky is definitely not the limit, but it is the visible limit that we see to date. I wouldn't have done justice without speaking about the institute that I am a head of, which is the Institute for Nanotechnology and Water Sustainability. We call it the Institute of Global Stage and Academic Excellence. And to the colleagues in the Institute, the 32 staff members, 26 academics, 5 technical team, and 3 administrative, you are collectively making us who we are, and we wouldn't be where we are without you. So the Institute of Global Stage and Academic Excellence, INANOS, Thank you so much for making us, and we look forward to a journey going forward. They do say leadership is a performance and a collective effort. And also to the students, the entire students of the Institute, not only just those under my supervision. I think those under my supervision only make about 10% of the entire student body. But the entire student body of the Institute, thank you so much for the support. And we look forward to interacting with you more going forward. Ladies and gentlemen, thank you so much for making your time, for attending this lecture. And I hope that you've been able to get a brief snippet and a brief preview of what we do as a living to answering innovatively addressing current and emerging issues relating to water scarcity and water quality. Ngiyabonga kakhulu, ndawuqala futhi ngigcine ngikubonga batali bami, ngibonge make wami elokhule ahlupheka kanye nathi. Ngibonge batali banakethu laba ngisupportile. Ngibonge umbanami, ngibonge nemngami, ngaphandle kwabo ngeke ngize ngibe lutho. I thank you.
Good evening, ladies and gentlemen. I would firstly like to thank the organisers and all at the University of South Africa for inviting me to act in this important role today, which is the celebration of Professor Thabo Nkambule joining the professorate to pursue his academic purpose and vision. So please do allow me to say a very big congratulations to Professor Nkambule for achieving this hugely significant milestone. So it falls on me to say a few words as the respondent to Professor Nkambule's virtual lecture and inauguration. So I will say some words about the topic of the lecture and try and place that into some form of international context. Now, Professor Nkambule's speech centered on a really important and crucial aspect of sustainable water supply and treatment, considering the abundance, the scarcity, and alongside the important role that innovation must play if we are to ensure fair and equitable and safe access to drinking water across the globe. And his research around these themes addresses his research is basically centered on the role that NOM, or natural organic matter, plays in resolving some of these very, very challenging issues. So I've been fortunate enough to have known and collaborated with Professor Nkambule and Professor Becky Mamba for more than 10 years now. And our collaborations have enabled us to share knowledge, participate in student and staff exchanges, and develop formal partnerships between our universities, and that's Cranfield here in the UK and UNISA in South Africa, of course. And indeed, these links and these collaborations have facilitated further international links with other colleagues in, for example, the United States. But throughout all of this time, the one thing, apart from the friendship that we have, that has brought us together has been the research, and specifically research on NOM, natural organic matter. So this one small acronym, NOM, plays such an important but perhaps poorly or misunderstood role in controlling our water treatment and supply systems around the world. So it can be truly recognised as a global research field, and a field that Professor Nkambule has become a recognised name. A point that has been driven home today through the lecture that's been presented by Thabo today has been the work where he's shown leading research into the characterization, innovative treatment methods, and some of the mechanistic insights into the chemical processes that are involved in NOM and its treatment. So the research framework that's been proposed by Professor Nkambule therefore tackles some really important aspects of water treatment, and one that is becoming ever more important and relevant as new regulations, sensors, and treatment technologies emerge. So we must be in a position to understand how these can be best introduced, and particularly in areas of the world where Tabo has focused his work, where there may be fewer resources available. So any decisions that are made around implementation and innovation have to be underpinned by the science and understanding. And I think that's where Tabo is really contributing. And as he has spoken about in South Africa and many other countries, these decisions have to be aligned with often very high levels of water scarcity and significant pressures on the availability of water resources, particularly when you have competing aspects associated with water use in agriculture, industry, and of course for drinking water. And so these are big global challenges and very much part of Professor Nkambule's research agenda. And these align very well with many of the World Health Organization Sustainable Development Goals as well. So Professor Nkambule has presented this framework today for research and innovation in this space that considers, firstly, our understanding. What is it that we're trying to treat? And secondly, what should we do about this? How do we innovate to make treating these water sources easier and more effective, while reducing the potential impacts of, for example, disinfection byproducts on human health? And as Professor Nkambule has noted, we are all exposed to NOM in drinking water. Every one of us who consumes tap water, even bottled water, is exposed to some degree of natural organic matter, and it's ever present in our water sources. And so this is a really truly global challenge, and one that occupies scientists right across the globe. What is this material? How do we control it? What important aspects control the removal of the NOM? Because in itself, this material is a relatively harmless group of compounds, but as Professor Nkambule has highlighted in his lecture, we know that it interacts with water treatment chemicals. We know that it can disrupt processes, for example, membranes, and cause membrane fouling, and compete with micropollutants for removal. It can be a food source for microbes, which then influences biofilms and bacterial concentrations. It colours the water in many places, and consumers don't like this. And I think has really been evident in the lecture given by Professor Nkambule. It changes. So from day to day, from season to season, from location to location, no one sample is ever the same. So we have this complexity of natural organic matter. And so from a characterization perspective, Tabo has developed and used advanced tools that help us establish how organic compounds are treated, what can't be treated, and what the general features of compounds are that are left behind in our final treated water. And so this includes these advanced characterizations such as hydrophobicity, charge, fluorescence, absorbance, etc. And so this is really at the cutting edge of research in this space. And the whole research area of NOM, as I've mentioned, is globally important. So since the 1970s, when we established the link between natural organic matter, disinfection byproducts, and the possible impacts on human health, the importance of NOM from water has grown significantly. So we're therefore very much obliged to monitor and remove it from drinking water to prevent significant process and operational disruption. And South Africa is really catching up fast with its neighbours and other locations across the world in this regard. And it really is that Professor Nkambule is leading this charge. And we know that NOM is changing. So much of Northern Europe and Northern America has seen increases in NOM concentrations in our water sources. But it's not just this concentration, it's also this compositional change. And this has happened for many and varied reasons. But we've historically had very few data sets on NOM characterization in South Africa and Africa more broadly. And Professor Nkambule has really developed that research agenda in terms of obtaining some of this information. And we should therefore be able to understand how the dynamics of NOM are changing from an African context. And of course, with that information, we have the power, and that's the power to improve water quality, and that's essential. The global recognition of NOM as an important research area is highlighted by the fact that the International Water Association hosts a conference on NOM. And this used to be every 4 years, but it's now increased in frequency to every 2 years as the global importance of NOM has become more understood. And it is in recognition of the work that both Professor Nkambule and Professor Mamba have had in terms of this research area that UNISA are hosting this event, hopefully to be held later this year. And that's a fantastic recognition of Professor Nkambule's work and leadership in this space. And we need better tools to increase the resilience of our water systems. So some of the specific research that's being read by Professor Nkambule that's been presented today really fits into this space and opportunity, presenting novel ways of removing NOM from water. For example, the use of high-performance membranes, harnessing nature for the removal of NOM using fungi and the associated enzymes, and developing adsorbents and specific photocatalysts has real meaning and importance for innovating in this important water science area. So finally, I would just like to say a few words about Tharbo's leadership and team building skills and kind of personal attributes that make Professor Nkambule an honourable recipient of this recognition today. And I think that's because really people have always been at the centre of what Tharbo does, whether that be looking after and supervising students or hosting visiting academics such as myself who've been really nicely hosted by Tharbo whenever I've visited. Other people have always been at the heart of how he works and operates, and as such he's been able to develop a great team around him that trust and respect him. And this has enabled him to truly deliver on his research agenda. But more importantly, he's nurturing the next generation of scientists and engineers that will continue the legacy of this important research agenda. So thank you very much for the opportunity to speak today. I continue to relish the opportunity of working together with colleagues at Nanos and in particular Professor Tharbo Nkambule. Thank you.
Thank you. What an interesting lecture you've delivered. An educational one, for that matter. That is an acknowledgement of the extent of your scholarship and its societal significance. Thank you, Prof. Nkambule, for your lecture. Thank you to the respondent for engaging us with such a response that furthers your scholarship. And thank you to your family, your loved ones, and your friends and colleagues for gracing this lecture. Without them, we would have had a different lecture. I want to thank you, ladies and gentlemen, for this support, supporting this lecture and supporting this work of Prof. Nkambule. I express gratitude also for all the comments that you've made, and invite you to even pose questions to the professor that we're installing this evening, and ideas of what else could he be looking into for his future research. Not least, I want to express gratitude to everyone, as I also concentrate on colleagues behind the scenes who would not have come to this podium, who've made this lecture a possibility and success. These are colleagues at an institutional level, ranging from colleagues in the Department of Institutional Advancement, the Corporate Affairs Unit, who've worked on all the logistics to ensure that we have the lecture of this kind this evening. Media colleagues who've put together this lecture, IT colleagues who've ensured that all of this runs smoothly, and the facilities colleagues without whom all of this list of very important admin support staff, this a successful lecture will not have had. I again express gratitude for your patronage and wish you a good evening. Goodbye.